To understand planes, you got to first understand how they're defined, and you know, when it comes to like definitions of curves and shapes, right? We think about, well, to make a circle, it's all the points that are equidistant from some sort of center. For an ellipse, it are all the points whose sum of distances from the foci is like a constant, right? So for a plane, this definition of like how you can create a plane is, well, if you think about it, right? Let's just make a plane, something like this, and you know, planes, they can extend, they do extend out, I guess, forever. Think about this, right? There's going to be, let's just say the plane is quote unquote centered or kind of like fixed, or you know, it passes through some point P, where P is your X initial, Y initial, Z initial, right? So it's at point P, well, you can make a vector from any other point on the line. So from point P right here, you know, this is a point on your thing, so I'll just call it point Q. We have a point here, and you can make these vectors, right, an infinite amount. And what do all of these vectors have in common? You know, they're certainly not the same direction, they're certainly not the same magnitude, but they're all orthogonal, or they all can be orthogonal to some sort of vector n that is directed out of the plane, right? So if my plane is my hand, this orthogonal vector is kind of sticking out, and it's perpendicular. So I'll call this n. It's perpendicular to every vector here, right? So it's perpendicular to all the vectors that start from point P and point to any point x, y, z, right, on this line, right? So you know, if we think about let's say point Q, right? Let's say this is any arbitrary point x, y, z on this plane, right? What we know, according to this definition of a plane, right? You know, it's all the points whose vectors starting from some other point to that point, they're all perpendicular to some sort of normal vector n. And if we use this definition, right, let's say that this point x, y, z from the origin is defined as, I'll use it. Should I just do that right now? Yeah, let me just do that right now. I dropped this little thing, which is kind of annoying. But yeah, it's dirty. I gotta clean that. Let's say this is some sort of vector r. So from the origin to p, x, y, z, or r initial, and then let's say r is from the origin to point Q, then this would be the same as r minus r initial. This is a difference in the vectors, right? Because if you do r initial, if we do tip to tail addition, r initial plus r minus r initial, you just get r. So using this definition of a plane, we can essentially get a vector definition of a vector equation for a plane. So vector equation for a plane, well, our orthogonal vector n is always going to be orthogonal to r minus r initial. And remember, r minus r initial, that's just a vector from our starting point to any other arbitrary point on this plane, right? It's not like literally from like it's not literally this direction. It could, you know, our initial could be this vector or this vector or this vector. It's just any arbitrary point. And because they're orthogonal, we know from dot products, it's going to end up equaling 0. So now, in terms of scalars, let's say n has components a, b, c, and we're going to use x, y, z, and x initial, y initial, z initial, right? So I know that, well, r minus r initial is going to equal x minus x initial, right? It's x minus x initial, the difference of the coordinates. Y minus y initial, z minus z initial. And from this, we can just use this dot product thing over here, right? We can do the dot product operation, A, B, C dot x minus x initial, y minus y initial, z minus z initial, all has to equal 0. And then when I do my dot product, I get this. So A minus x minus initial plus B y minus y initial plus C, I always mix those up, C minus, or C times Z minus Z initial is going to equal 0. And when I distribute over my x's and stuff, so I have this AX plus BY plus CZ plus D is going to equal 0. And what is D? Well, D is really the, it's going to be like when I distribute the A over to these constants, because the x initial, y initial, z initials, those are just constants. It's going to be all of my constants. So it's going to be negative xa initial minus by initial minus cz initial. So this, I think, is the most important thing to know. This is the equation of a plane. All right. So just to kind of understand this equation a little bit better, your coefficients in front of the variables x, y, and z from this vector equation of a plane, and by the way, we call this a linear equation of a plane. No, it's not like really a line, but they're all of orders of 1. So in the same way that a line is like a linear equation, I guess, of a curve, the plane, this is kind of the linear equation for a plane, which doesn't really have any curves, right? So the coefficients A, B, and C, they tell us the direction of this plane, right? Because remember, this comes from the normal vector. So the A, B, and C tells us the components, right, of the normal vector. So I know, hey, if my plane only has, so consider this is really a plane, right? 3y plus 4z is going to equal 0, right? For this plane, I know my orthogonal vector has components 3 in the y direction, 4 in the z direction, but it also has 0 in the x direction. So I know my vector will probably look something like this. So 3y, 4z, right? This is what it's going to look like, and it's going to look like this, and it's kind of hard to visualize this, but there's no component in the x direction. So I know my plane will not be facing the x direction at all. It will instead be kind of in the x plane, I guess. But I guess really in this case, it wouldn't. It doesn't really look like that. How did the book say it? I kind of forgot. Let me check my notes. Maybe I wrote it down. No, of course I didn't. Why would I? But the point being, though, is this tells us direction, right? I know the 4z tells me it's kind of slanted up. The 3y tells me it's going to be, oh wait, I drew this wrong. Did I draw this wrong? No, I didn't. Yeah, no, I drew this right, my fault. But the 3y tells me it's going to be slanted in the y direction, right? It's going to be kind of slanted, I guess, to the, I guess it's not as clear as up. But hopefully you'll kind of understand the orthogonal vector tells us direction. So these components tell us direction. The D kind of gives us kind of an idea about what point it's passing through. So I know that, hey, y and z, like I know if when x is 0, y is 0, z is 0, then it's going to be equal to 0. So I know that the origin 0, 0, 0 exists on this plane. However, right, if we define, so when we're writing our equation, right, this x minus x initial stuff, if my x initial, y initial, z initial, if it's not 0, 0, 0, if it's not the origin, then I know it's going to be passing through some point, and that's what kind of creates the D constant in the equation. So if I change this to 9, if I change this equation to 9, then it's still going to be two parallel. They're still parallel planes because their orthogonal vector 3, 4, 9 would still be they would still be parallel, right? If the orthogonal vector of one plane is equal to the orthogonal, and orthogonal means perpendicular, I probably should have clarified. If the two orthogonal vectors are parallel, they're going to be, the planes themselves will be parallel, right? Hopefully that kind of makes sense if you kind of visualize it. I know that it's a little hard to visualize things. It's even harder to really draw them. But yeah, if I try drawing this, I guess I didn't draw it perfectly parallel. But you can see if the orthogonal vectors are parallel, so will the planes be, assuming that I drew it better. Now, if the planes aren't parallel, and I get something like this with two planes, well, believe it or not, if I were to extend this normal vector and like this angle between the normal vectors actually ends up being the angle of the two planes, right? That's the angle in between them. So, yeah, that is kind of to give you an idea of like how you can kind of interpret a plane based off the equation. And you can figure out the intercepts, right? I know that we're going to have a z-intercept when, we're going to have like a z-intercept when z is equal to 0. And you can kind of solve for that. Let me just think of if there's anything else I should state. No, it's not when you set z equal to 0. Or is it? Well, I guess, yeah, it is when... No, it's not when z is equal to 0. I'm so sorry. That's not what a z-intercept is. Okay, let me just scratch that. No, I just thought about it. A z-intercept, right, when it intercepts the z-axis, that's when your x and y is 0, right? When your x is 0 and your y is 0, I know the point's going to be something along the z-axis. To find your y-intercept, set x and z to equal to 0. So on and so forth. And yeah, you can use the equation to kind of get an idea of like what the plane will look like. I just want an example. So now that's really all with planes. There's also the distance formula, which in my honest opinion, I don't see much worth in really knowing. I don't know. It's just a good formula to know. So here's the distance formula. I'm just going to, instead of wasting time, I'm just going to show it to you guys. I don't think you guys are too interested in this. You can always Google this formula. But the distance d from a point to a plane is given by this formula. So you just do so you do like the x coefficient multiplied by x1, the b coefficient multiplied, or the y coefficient b multiplied by y1, so on and so forth, and then do some sort of square root at the bottom. You could probably Google that. I'm sure that's not like, your main concern. I gotta understand where that equation comes from. I actually want to try to derive it. But it comes from the idea that your distance from a point to a plane is defined as like the closest distance, because from a point right here to a plane, you can do a distance here, you can do a distance here, but it's when you're like orthogonal to the plane, right? It's like the distance like directly towards it without any angles or whatever. It's completely straight directed at the plane. That's what we define as, I guess, the distance. Let's go over an example. So let's say we have a line, and this line is given by, so first let me draw an axis. So this is our little axis we can use. And we have a line, it's defined by x is equal to 2y, which is equal to 3z. So this is a symmetric form of the equation of a line. And I gotta keep remembering to add the dot just to differentiate, or the little dash in the z. But we want to find an equation of a plane that contains this line, and that also contains a point 1, -1, 1. So to first get an idea of how to go about doing this, right? I want you to understand what this is really asking, right? Because you can draw some sort of line. This is not the line specifically. Actually, I guess we can make it that line specifically by having it pass through the origin, but it doesn't really matter. That's terrible. Draw that again. So let's say we have a line passing through like this, right? So to have a plane pass through this line, it's actually not too bad, right? Because you just need to find a vector. So let's just say n equal to a, b, c, right? You just need to find, I'll just do this example because I think it's a pretty good example. But you just need to find some sort of vector n that is perpendicular, so I guess I should draw that better, perpendicular to the line, and there are an infinite amount, right? There are really actually an infinite amount of vectors that are perpendicular to the line. Because if this was my line, I could just do a vector here, there's a vector here, vector here. But so to find this vector, all I do is I'll say, hey, I know this ABC needs to be perpendicular to the vector that defines the line's direction. So remember, to get it in form, I know x will equal t, 2y will equal t, 3z will equal t. So I know y is really 1/2 t, and z is really 1/3 t. So I can kind of say, hey, the directional vector, right? It's going to be 1, 1/2, 1/3. Remember from our equation of a line, those coefficient kind of tells us the vector and the direction of the line. So I can say, hey, I know that a, b, c dot 1, 1/2, 1/3 needs to equal 0. Or in other words, a plus 1/2 b plus 1/3 c equals 0. And there's actually, you can just think of any solution, right? You could say, well, maybe b and c are equal, and then you can solve for a. Maybe a and b are equal. Maybe c is 0, right? And then you can solve, I guess you can't really do that. But yeah, you can very easily, like you can find a solution to this kind of a thing. You get an infinite amount, right? You could do b is equal to 6, c is equal to 6, a is equal to 5. But the condition that gives us one exact answer to this question is the fact that 1, -1, and 1 also needs to be on this plane. So now what you have to kind of think about is, well, hey, how can I get, so let's think about this, right? I'm going to draw a vector from from the origin, which I'm choosing the origin not because I'm going to do it every time, but I'm doing it because I know the origin exists when I plug in 0, 0, 0, or if I plug in t equals 0, then I can get the origin. If the origin is not on this line, you could just get your parametric equations and be like, okay, at t equals 0, right, what are my x, y, and z values, right? So let's say if it was instead y equals 1/2 plus 5, I know at t equals 0, it would be 0, 5, 0. Hopefully that kind of makes sense. But I basically say, hey, my initial point is 0, 0, 0, right? At some point on the line. And 1, -1, 1, that's a vector. So I can say from 1, -1 to 1. So for something like this, right? So this is a point 1, -1, 1. What is so this vector, so let's just call this vector v. Let v equal, so 1 minus 0, -1 minus 0, 1 minus 0. Or just 1, -1, 1. It's nice because the origin is included. Well, hey, what is a vector, right, that is perpendicular to both 1, -1, 1 and our line x, or I guess the vector of our line, which I kind of erased. So I'll let v2, so let v1 equal that. v2 can equal 1, 1/2, 1/3. What is a vector perpendicular to both of these, right? Because if I can get that vector, right, that's going to be perpendicular to both. I'll draw it like this. Then I can get an equation of a plane using this vector and then using this point as kind of the point that it goes through. So how can I find a vector that is perpendicular to two vectors? Remember, there is an infinite amount, right? Because this vector can be of any magnitude, but one surefire way to get a solution is you doing a cross product. Cross products are always perpendicular to both the vectors you are crossing. So v1 cross v2 is going to equal, let's do our determinant, I, j, k. So 1, 1/2, 1/3, and then 1, -1, 1. So I'm just going to do this in kind of my vector form. or I guess, yeah, sure. So for I, if we're doing, for the I component, or the X component, it's 1/2 minus 1/3, or sorry, 1/2 minus negative 1/3 when I'm taking my cross product. So that would actually be about 5/6. For the J component, it's going to be 1 times 1, 1, minus 1 times 1/3, 1/3. So 1 minus 1/3 is 2/3, but it's going to be the negative of that because the J component, remember, the Y component's the negative when we're taking the determinant. So negative 2/3. And then for K, we're going to do 1 times negative 1 is negative 1. 1 times 1/2 is just 1/2. So negative 1 minus 1/2 is negative 3/2. All right. Now, just for giggles, let's just say, hey, what if these fractions had 6 as a denominator, right? Well, I'd have 5/6, and then I would have negative 4/6, right? Those are equivalent fractions. And then negative 3/2, I would have the same as negative 9/6. And hey, right, this would just be, this normal vector would just be parallel to 5, negative 4, negative 9. Right? I can just factor out a 6, and I know they'd still be parallel because they're just, they're like, what's the word? I guess multiples? Like, these are, like, if I multiply this by 6, I just get this, right? So I know they're parallel because they're just scaled up versions of each other. So this is perpendicular to these two, and this is parallel. Then I know 5, negative 4, negative 9 is also perpendicular. So now what I can do is I can make the equation of a plane. I can say, hey, 5 times x minus, let's do a starting point 1. So x minus 1, right? Because we're using 1, negative 1, 1, given from the problem, minus 4y plus 1, right? Because I'm doing y minus y initial, so negative 1. Y minus negative 1 is the same as y plus 1. Plus, or minus, I guess, because negative 9. Negative 9 z minus 1, all needs to equal 0. So I get 5x minus 4y minus 9z. And then if I have, now I got to worry about the coefficient, or the constants, right? So negative 5 here, right? 5 times, so I just write it down. Negative 5 minus 4, right? When I distribute the negative 4 over. Negative 9 times negative 1 is just positive 9. Going to equal 0. Hey, negative 5, negative 4, negative 5, negative 4 is negative 9. Negative 9 plus 9 is 0. So this, the whole constant is just equal to 0. So it's just 5x minus 4y minus 9z. Why does that make sense? Well, hey, that makes sense because 0, 0, 0, the origin, right, is contained on this line, and therefore it's going to be contained on this plane, because our plane needs to contain this line, x equals 2y equals 3z. So yeah, this has been planes. Yeah, let me know in the comments, I guess, if you have any questions. I think hopefully this was okay, only 23 minutes. That's like shorter than usual. Not bad. I forgot to press stop.